Hello, Janardhan. Is it audible?
Clear, sir. Audio is clear.
Thank you.
What about me?
Yeah. Your audio is also
Yes.
very
Okay,
clear.
thank you, sir. Thank
Your audio is clear, sir. Perfect. Fantastic. Marvelous.
Good afternoon, sir.
Good afternoon.
Murthy sir, good afternoon, sir.
Good afternoon. Good afternoon. Hello.
Sir. Sir, 5 minutes, sir. We're going to start the session.
Okay. Okay. Yeah.
I request all the participants to fill the attendance link given in the chat box. Madam, unmute yourself, madam.
Good afternoon, sir.
Yeah. Good afternoon.
Sir, we are thankful, very much thankful for, sir, to you, sir. In a
No
short span
problem.
of time, you have accepted our invitation.
Yeah. Yeah. Many people are working in your organization are known to me.
One second, one second. 1 second, sir.
Yeah.
Thank you very much, sir, once again.
Thank you. Thank you. Thanks for having me.
I think still we have time. We can wait for
Yeah.
2:45.
Yeah. Sure.
Yeah, yeah.
2:40. That's right.
The session is going to start soon. I request all the participants, please fill the attendance link provided in the chat box.
Start. Welcome back to all of you for the second day post-lunch session of the event, International E-Symposium on New Frontiers in Chemical Sciences. There is a change regarding the speaker, Dr. Sadhana Railu. She is unable to make today's presentation due to unavoidable situation. Instead, we have an eminent speaker, Dr. Tekmurthy Chavali, who is expert in sensors, nanomaterials, nanopolymer composites, nanothin films. I profusely thank Dr. Tekmurthy Chavali for accepting our invitation. This is a session where the audience may be experiencing post-lunch slump, the moment right after the lunch, which is one of the most challenging moments for learning. But I'm very sure that Dr. Tekmurthy Chavali, who is so influential, that we are going to raise our spirits high and participate actively and submerged in the topic. Thank you, sir. And with a brief note, I request Anima madam to take over the session. Anima madam? Okay. Okay, with this brief note, I request Dr. K. Venkatratnam sir to introduce about the speaker. Over to Venkatratnam garu.
Thank you, Dr. A. Ratnamala, convener of this GITAM-IEON-2020. It's a privilege to introduce one of the eminent scientists of India, Professor Dr. Tekmurthy Chavali. Professor Dr. Tekmurthy Chavali had over 24 years of research experience and 19 years of teaching experience. He guided 18 PhDs, 3 MPhils, and 5 postdoctoral fellowships. In the year 2014, he was selected to the top 40 analytical scientists of the world by the survey conducted by American magazine, The Analytical Scientist. He published over 212 articles in the fields of sensors, nanomaterials, nanopolymer composites, nanothin films. He's responsible for over 150 technical reports and books, book chapters, written for various purposes and delivered around 186 invited talks, lectures, both at national and international levels. He was a co-principal investigator, collaborator, reviewer for several national DST, Fast Track, UGC, CSIR, DRDO projects and international projects, DST International. In the last 10 years in India, he had completed 7 research projects around worth of 3.85 crores. Previously, Dr. Murthy served simultaneously as Professor of Analytical Chemistry and Nanotechnology, Dean, International Relations, and also as a Director, Center for International Affairs at VFSTR Dimuttubi University. Dr. Tekmurthy at present working as Professor and Director at SVRM Nagaram. With the gist of information about Dr. Tekmurthy, I will hand over the session to Dr. Tekmurthy. Sir, please share your screen.
Thank you, Venkatratnam garu.
Sir, thank you.
Hope the audience can see the screen.
Yeah, sir, it is visible, sir.
It is visible. Okay.
Yeah.
So I'd like to commence, right? Okay. Thanks for having me here in this particular EON International Conference on New Frontiers in Chemical Sciences. I'd be very much thankful to my colleague, Venkatnath Garu, and your faculty member, my student, Dr. Janardhanan, and also some of the speakers who are also my students and my colleagues earlier. And in this particular topic, I'm going to talk about nanomaterials for sensing. Instead of calling this as a sensors, I'm going to speak specifically about the nanomaterials. Why do we need nanomaterials? And what is the type of devices? How do we frame them? How do you produce them? How do you manufacture these materials in sensing most of the problems that we get from industrial orientation? And in this particular lecture, where I'm going to talk about a little bit about 1 or 2 slides about me and some of the exclusive works that we do in our laboratory, plus what are the miniaturization methods and why do we need miniaturization? Once you miniaturize, you need to have certain materials in the nanoscale for extraordinary properties. And why do we need nanomaterials for sensing? Why do we sense? And at the same time, what are the benefits that you are going to get when you miniaturize and use nanomaterials as a sensing device? As I was told, presently I was working as director of PG studies of Nagaram College. And in this particular lecture, where it is going to be segregated into 4 sections, I'll try to limit this particular thing well under 40 minutes, because this lecture has been prepared for students of PhDs, first year and second year, and then for applied nanotechnology students where they have to develop their own substrates, materials, integrate them with the chemical sensing technology, with electronics, and further it has to be packaged and sent to the commercial setup. So in this, I'm going to talk a little bit, very brief, not more than 1 to 2 minutes about our research group, developments, key technologies, and why do we need miniaturization, and what are the concepts in nanotechnology, sensor chip layouts, architecture, what are the materials that we use for different sensors. I'm not going to talk about all the sensors that we have developed or developing, but specifically which has given a lot of impetus on the global scale. I'm going to give those examples and how these are going to be useful for biotechnology, bioinformatics, hospitals, chemical laboratories, semiconductor industries, etc., etc. And at the same time, I'll try to give some of the MEMS and NEMS devices as examples, plus some of the sensor chips that we have developed for polymer composites, polymer thin films, and hybrid materials, gel metal oxides, triple metal oxides, etc., etc. And also I'm going to touch upon the sensors, how it is going to how do we confront this particular sensor, and also what is the comforts that are going to get in day-to-day life, either it is an office or a house or industry or whatever it is, and some of the selective examples, what we are at present doing for bio nanotechnology sector. And finally, I'm going to summarize with references and overall gist of this particular lecture. Yeah, as I said, I was working in one of the PG colleges. Previously, I was with VFSTR University, and after that, I moved to this particular college where it is serving as NAC A grade since 2014, and it is also an ISO accounted, and it is an autonomous body where they have a lot of inspiration given to their faculty to conduct R&D facility. Yeah. Since I'm an analytical chemist, basically from MSc from Jawaharlal Technological University, since then we moved into different areas, environmental chemistry, optophotonics, devices and circuits, because this is one particular area where we were completely alienated. So we have to learn, we have to develop the group so that we can integrate at the nanoscale with the materials and electronics and develop the devices and circuits. And fortunately, we'll be able to commercialize them and patent them. So typically, I call myself as a chemist with applied nanotechnology background, since we are going to apply everything. And whatever we do not in bits and pieces or in sections, but we start from basic material development to sensing, wireless sensing, wire sensing, and at the same time device fabrication, packaging, and then patenting. I'll give 1 or 2 examples what we have developed over a period of last 2 decades. And in addition to that, we have biotechnology, civil engineering, where applied nanotechnology is going to come into picture for certain things where we aid in our technology from my group, and we develop so many things. And over a period of last 10 years, some of the key technologies transferred to
Hello.
So, sorry, audience. There is a small technical issue from the guest speaker side. So, wait a minute. Sir will join again in the session. Meanwhile, all the audience, I am requesting to fill that attendance link.
Sir, please unmute yourself, sir. Okay. Sir, unmute yourself, sir. Dr. Professor Murthy Chavali garu. Please unmute yourself.
Yes, is it visible?
Yeah, visible and audible, sir.
Oh,
Yeah, visible, sir. Proceed.
Yes.
yeah, sorry for inconvenience. And coming to the key technologies that we have developed in UV-induced in situ photopolymerization to electrocatalytic oxidase mechanisms and visible catalytics and so many other things, and lasers and MIR lasers, fabric period, gas, indium, aluminum gas, solar electrodes, plus the primary standards in the metrology and COH systems, plus so many other things. These are some of the things that we have developed in the due course of time. And as we have already shown, discussed these things, coming to the primary part, why do we need miniaturization? Most of you know what is meant by miniaturization: scaling down from macro to micro, which is nothing but miniaturization. But why do you need this? It has its own advantages and it has its own disadvantages as well. Though advantages are much more prominent than the disadvantages. I'll show you a simple example. This was the flash drive, which is 32 MB, which is costing around 9,000 rupees in 2002. And now we have come down to 2 TB, which is also a flash drive in 2020. And this is going to be by 2024, 64 terabit. See the size remains the same, but the volume and the capacity that is going to be involved or absorbed, the data is going to be huge. It has been multiplied by almost 300 times. And if you take some of the SD cards, 2005 it was around 128 MB, and then in 2014 it got up to 1 terabit, and in 2020 it is going to be 1 terabit, and previously it is 128 GB, and so on and so forth. These are being helpful by miniaturizing or reducing the tracks between these particular materials using the nanomaterials. You are going to increase the capacity of these devices, and at the same time accommodating so much of the information and so much of the data that is required to build into this flash drive. That's why miniature is one of the most important thing that is required for many purposes, either in chemistry or physics or whatever it is. And if we talk about SSD drives, SSD by 2020, it is going to be, it is already 100 terabit, which was developed by Nimbus Data. And in 2018, the hard drive has gone up to 15 TB by Western Digital. So these are some of the huge things that miniaturize gives us an advantage. Another most important one is you can see so many miniaturized devices over here. The first and foremost important thing, once you scale down from the macro to miniature scale, it is going to minimize the energy consumption, and at the same time, the errors or the redundancy which is existing within these devices and arrays are going to be lessened. And at the same time, you can integrate into the small space 2 or 3 devices instead of holding the entire thing in a large space. You can integrate everything, their electronics, their sensing schemes, etc., etc. And once you reduce the size of these devices, it is going to be less in consuming power, and these are going to be faster because of ROM and RAM capacity, and it is portable, and it is going to be way less in weight, so easy to carry, especially in the sectors of defense. It's very, very easy to carry, and it also gives an alarm signals where harassed materials are going to be in place. Definitely, there is going to have servers in a military purpose. And at the same time, like in macro devices, you can also have smaller miniature devices, 1 or 2 sensors, or covering over a large dynamic range. That means ultra PPQ levels, parts per quadrillion levels to ppm, and even more in percentage levels can be utilized or detected by using this miniaturized devices, and possible integration in the future with the new developments that are going to appear. So these are some of the advantages you have. And in terms of engineering, if you take, it is low energy, little material is consumed, and at the same time you can have array of sensors, improving your signal sensitivity to the highest possible level. Once you change this micromaterial to nanomaterial, your signal is going to be further encouraged or enhanced. So you can do very, very little less error prone devices with these miniature devices. And at the same time, it is lower in cost, and it also can be disposable. And so many other things will be utilized by miniaturization. And it has a lot of potential impacts and also negative impacts. Negative impacts are much less compared to other. The most important negative impact is going to be the material toxicity. Why we are talking about these miniaturized devices? Because in USA, when I was a student, people are developing the first time miniaturized devices. That was way back in 1996 and 97, where they have produced a NEMS gas chromatography. It is almost the size of 1 to 5 centimeters. And this does the purpose of the entire thing, where the same thing has been developed into a DNA assay chip, where it does exactly the laboratory, what a laboratory does in a real world has been done on a single chip of 1 inch in size. The design, architecture, assembly, integration, packaging are exactly similar to the macro devices, but it has its own advantages. It's faster in response, and at the same time, it gives very, very reproducible and sensible results. And with that improvement, we thought of developing, since we are in the mid-infrared spectroscopy group, we thought of collaborating with one of the FTR makers, Brooker, and we decided to develop a miniaturized spectrophotometer, almost in the size of 2 feet. That time it is called a miniaturizer, but we were able to develop some sensor using spectroscopy, using chemical sensors for undersea based application, because this all the parameters are being measured undersea. And this is the typical architecture what we have designed, developed, and integrated with the existing electronics. These electronics were not developed by us, but it was integrated with the existing FTIR system. Only thing is layout, optics compartment, and the sensing head, everything has been modified. With this, we started, and finally, we ended up in developing a ultra-sensitive parts per quadrillion level FTIR, replacing the source, replacing the detector, which is an MCT. Source is a commonly available silicon carbide, and sensitivity has been increased by having a hollow waveguide plus a Winston cone, which improves. The entire thing is going to be the 5 millimeters in size and 1 millimeter in thickness of this particular hollow waveguide. With this, we were able to detect something in the orders of parts per trillion to parts per quadrillion level with a very, very good accuracy and very fast results. And this has been combined with interferometers later to study and compare this particular thing. And at the same time, Scott D. Collins of University of California, Davis, where he had developed an entire interferometer of the size of 5 millimeters. And it gives exactly the same as the available MIR FTIR. The signal remains the same, and the interferogram also remains the same. So when there is such a device where it can be economical, fast enough, and with all these ideas, Oriva has come up with the smallest FTIR where they utilized avalanche photodiodes so that it is making much more smaller than the existing things. And some of the smallest things, as an examples, you can see the tiny heart, which is on the fingertip, and you can see fingertip sensor. You can see smart ITS project, and you can also see the smallest capsule, which is equivalent to an endoscope, and a jet propulsion center sensor, which is almost close to the dime, and a beat tracker. All these things, or macro things, have been reduced to miniaturized scale with its own advantage. Coming to chemistry and physics, you have a silicon resonator nanostructure. You have medical telesensor chip on the fingertip where you can see it can measure, transmit the body temperature to a particular node without doing anything like a macro thermometer. And you also have a micro cantilever and IR spectrophotometer for blood analysis. This also can do the blood analysis, and it can also do gasoline octane analysis, and it can also transmit to a certain node where it is required. Like this, the miniature has reduced the entire 1 meter typical bench scale trials into 1 millimeter micro optical bench with again with the same set of parameters and same usage. And once after miniature, we are going into the nanoscale. Why? Because we are trying to enhance the sensitivity, and also you are trying to reproduce the same thing. Here is a very clear picture of a natural nanoscale and man-made nanoscale things. Just for your comparison, most of you might be knowing it, but still, to put you back into the nanoscale from macro scale, I've kept this particular slide so that you will have what is the scale difference between a virus or a bacteria or a nano or micro. And coming to nanotechnology, why do we need this nanotechnology? Because it encompasses science, engineering, and technology at the nanoscale. But at the same time, nanoscale has its own unique properties where it can give definitely specific benefits. Like smaller the nanoparticles, they may change the color, and the larger may change into another color. And at the same time, some of these materials, just by twisting, they can change the conductivity or resistance of these particular materials, so that itself gives us a signal to sense something. So all these physical sensors or chemical sensors, once you functionalize, you're going to be at some point of future. Industries are also going to predict all these things. And the reason why we need nanotechnology is it is an integration, and it is merging the boundaries between life sciences, chemistry, biology, materials, and also some part of the engineering. Typically, it was said it is integrating the biological principles at the same time, combining the laws of physics and also combining the properties of these particular chemicals with other subjects. That's why it is going to be a key enabling technology. And with its benefits, you can see this particular picture. You have just the black line is nothing but our hair, and the red entwined to this hair is silicon nanowire, which gives us a clear picture that these nanowires are much smaller than smaller than our hair, slender, and at the same time it is flexible and it can transport material or it can transport optics from one end to other end, being flexible. So with this one particular property, you can think of so many applications in physics, optics, photonics, biophotonics, bioinformatics, and even data transfer and computer science and other things. So with these things, this nano is also booming up in the entire nanotechnology market. You can see any sector, it has in billions of dollars. So this is one of the key enabling technology that helps everybody in market size, boosting the materials and improving the physical and chemical properties. That's why these low-cost materials tailor-made for a particular problem or as a particular device, engineering integration with electrical and electronic sections. These are very, very important, and these can be controlled by manipulating at their lowest possible level. You can functionalize them, you can make it into a different purpose, you can arrange them, assemble them to get the property that is of your interest, especially functional properties. And before doing, though these are toxic materials, before getting into this, these can be studied on the molecular level, and the theoretical studies can be done, or molecular studies can be done using different software, so that bench work can be avoided directly getting into application-oriented section. So, as I said, some of the unique properties of these nanomaterials include completely different from their macro scale. For example, opaque substance become transparent. Example, copper. Inert materials become catalysts. Platinum is one of the best examples. Stable material turns combustible. Once you convert aluminum into nano, it immediately becomes explosive. And solids turn into liquids at room temperature. This is nothing but gold. Insulators become conductors. Silicon is one of the best examples. So all this, without changing the material, all these properties can be controlled, differentiated, distinguished for our particular application. So let us try to utilize these properties at the nanoscale and develop different types of sensors, how we have progressed over a period of time for different sensors. I've taken from one category, one example, so that you will be able to understand. Before that, I'll get into sensor chips, what are the types, how you are going to do, because except the substrate, rest everything has been developed in our laboratory, and we produce them, we make the contacts, we overlay them, we overlay the transducing material, and we integrate that with, though it is a very crude method, still final product is going to be a much packaged, defined one. That also I'll give one example for diabetic sensing. And coming to another important point of these nanomaterials and nanostructure, this is one perfect example where you can see the characteristic length in a solid state science model. Scale length is this one on the last column, and the field of subjects is going to be electronics, magnetic, mechanics, and it has a very enhansive property which is at the center. And this enhancement has been obtained by this particular material only in the length regime. And all these length metrics are going to be nanometers. So once you get back to nanomaterial, you're going to have enhanced properties in various subjects. And you can also see different types of structures of one single material, which is zinc oxide, which is being developed not by controlling so many parameters, just by altering one single parameter, that is temperature. So by altering temperature, you can produce different types of nanomaterials and at the same time different types of nanostructures. Each structure could be useful for one type of material sensing because it is going to vary in its volume, length, surface area, etc., etc. It requires the skill, and at the same time, once you integrate this or combine this with dual metal oxide, I mean two are completely put together, you are going to get a different set of properties. And as I said, just by temperature variation, you get different types. And if you take another parameter as pH during the chemical reaction, you will get different types of structures. This is also a perfect example for zinc oxide. You have 4 different types of nanostructures, but in case of temperature, you have almost 12 different types of nanostructures synthesized just by varying a temperature parameter. And why do we need these sensors? These sensors, not just for chemical sensing or just to identify what is the content, what is the quantity of this particular gas or chemistry, chemical, or whatever it is. It has its own benefits. Sensors are required everywhere. It might be required for a social concern where at the boundary of your country, air and water are going to be safer and secure. Otherwise, it gives a social concern for the neighboring country. And it was also going to have a legislative concerns like breathing safe air and unpolluted air, and at the same time drinking potable water, health and safety, environment, avoiding prosecutions. These are some of the legal issues. And technological. Improved performance of the sensor require different types of new materials for the same sensing scheme, so that today you are measuring parts per million, tomorrow parts per billion, and then it goes on, parts per trillion, parts per quadrillion. Right now, people are working at parts per quadrillion level. And sometimes you will have transport repollution. It's a huge, like we have a swamp of insects recently. Like this, if you have a transboundary pollution, that can also be controlled by sensors, or at least monitored, and we can say who is the culprit, who is the suspect. And also we can have economic reasons for sensors. So all these particular social, legislative, economic, technological, political, these are the driving factors for the development of this particular sensor. That's why we need different types of sensors. You have sensors in industry, sensors for security, sensors for safety, which tells us not to go into that particular direction. Sensors for environment, air, water pollution, hazardous materials, sensors for healthcare, diabetic, insulin sensors, and also sensors for transport. Transport in the sense for transporting food material, transporting fresh produce, transporting vegetables. You all need sensors which is being monitored by RFID technique in electronics. So you need all these things. And if you take one particular example in one particular section, you are going to understand how many types of sensors are available. For example, if you take a smart office or smart house, without our knowledge, there are so many sensors in our own office or in our house, where you have a heater for monitoring the temperature, monitoring chillness, and also you have an automatic notifier, you have a remote controller, which is an infrared sensor, lighting control device, where you can dim the lighting once it is excess, where you can control the window shades, you can control the air and moisture for environmental. You can open the door without moving from your seat. So motion detection center where it switch on, switch off lights. And also if there is any smoke, it detects smoke sensing alarm. All these sensors are available. Typically in a house or a smart office, you will have none less than 25 to 35 types of sensors without knowing that they are existing. And at the same time, we use automobiles. And if you use automobiles, there are around 135 types of sensors within the automobile. So whenever you want to enhance, whenever you want to have a particular thing in your automobile, then you need to have a sensor. For example, you want to reverse the automobile, then you need a reverse window, a window for the rear screen. That means you are going to have a sensor which can think of immediately and project the rear view without even turning back. So in smartphone, you have so many sensors, for example, 15 to 25 sensors. And even nowadays, robotics, mechatronics have come, and even reaction is also being monitored by 10 to 15 sensors simultaneously for the mass production. So you have sensors everywhere. What are the typical sensor characteristics? A sensor cannot be just by detecting the quantity. It cannot be a sensor. It should be precise, it should be accurate, it should be stable, it should be reproducible, it should consume low power when you are producing in bulk, and it has to be inexpensive when you are marketing it. It should be compact, easy to handle. Since we may have arrays, it must be robust and smart. It should think by itself whether to take a decision. So now the smart sensors are coming up with artificial intelligence and so on and so forth. So this is a typical sensor, polymer sensor. Once it's developed, the connection between these things are broken, either the conductivity or the resistance will change over a period of time. This is a typical example for most of the sensors where we measure resistance, and you can get perfect dynamics and linearity of this particular sensor. So these are the typical parameters that you need for sensing. And another important factor, you need 3S and 3R, sensitivity, selectivity, stability. Without this, you cannot commercialize, and you cannot market your product. And at the same time, it has to be reliable, repeatable, reproducible. All these are standards for any sensor, so that you will get a perfect textbook type of dynamics for gas on and off statistics. So some of the nanomaterials. Before we get into nanomaterials, let us see some of the sensor chips. A sensor chip is interdigitated comb-like electrode without any connection between these two. Actually, this network of sensors, network of this material is made of gold with a platinum tip, and these are not connected. The connection between these two electrodes will be our transducing material, which is going to sense our interested gas or analyte or whatever it is. There are different types of sensors. All these sensors have been manufactured, screen printed in our own laboratory. Typically, this particular sensor for sensing anesthetic gas we have prepared, we have two gold electrodes connected by platinum electrode, and this is connected to the electronics device, over which we cover this or polymerize the polypyrrole material on this particular chip so that it can in situ UV photopolymerize without any problems of humidity or any temperature. And some of the sensors that are going to work at the highest possible sensitivity, they need the high temperature because they work only at above 120 degree, 300 degree or 200 degree. For that, you need a 2-electrode system beneath the sensor chip so that you will be able to heat that using ruthenium oxide or any other material or just a heater. So all these types of sensors are available with different areas, detection schemes, sensings, and everything put together. You will have a different layouts, and depending on your requirement, space available in your micro sensor, you are going to change the layouts and architecture within the sensor. A typical sensor chip looks like this, with transducing material on the top, and if required, a heater below, which is all just under 2 millimeters or 3 millimeters. This is the graphical representation. There the transparent material is going to the sensing film. In this case, we have polypyrrole and used scattered with multi-wall CNT. You have gold electrodes to alumina substrate, platinum substrate. Entire thing is 10 into 5 millimeters. And alumina substrate is the one which has been procured from outside commercially, and rest everything has been prepared. This is the typical sensor chip where most of our sensing studies have been done using this particular chip just by altering the surface area of this functional material. What we exactly do is we develop the chip, check for any mistakes or errors, and then we coat that with transparent material, and then we do the calibration. We check the sensor dynamics. And at the same time, we use different types of materials where for having enhanced sensitivity from nanohorns, nanopipes, etc., where we have tried different materials for CO, NO, CO2, NH3, and so many other gases. Typically, we started with CO sensor, carbon monoxide sensor. We ended up developing initially with 500 degree temperature, but somehow we were able to succeed with room temperature CO sensor, and this has been published, and one patenting is also pending. And we have a typical very good sensor dynamics, on and off characteristics, and interference were also studied with methane, hydrogen, and other things. And typically this material is nano cobalt oxy hydroxide material using hydrothermal material. As I said, on the beneath you have ruthenium oxide for heating initially, and this has been removed over a period of 1 year so that we'll be able to have sensing at low levels, low temperatures, like room temperature. Another sensor where we tried is with SnO2, tin oxide, and titanium oxide. We could not get the proper results. Proper results in the sense we got the results, but these are not accepted by the industry. So we combined TiO2 anatase type materials, SnO2, in 1:8 ratio. Different ratios have been studied, But finally, we ended up in having a very good sensitivity of 250 and T90 of less than 70 seconds. And this has been prepared and been commercialized earlier. So this is another type of ozone sensor that we have developed in our laboratory. And then we thought of developing a nitrogen dioxide sensor. We have very good results using indium oxide and tungsten oxide, dual metal oxide nanofilms over this particular electrode. And all these materials have been prepared by hydrothermal method. We ended up developing an NO sensor instead of NO2 sensor. For NO2, later we removed indium oxide percentage from this, which is 1:4. And using CNTs and multiple CNTs and tungsten oxide, we were able to develop a different sensor for NO2 gas sensor. The typical sensor dynamics are in the range of 100 to 10,000 ppb, where you can see these particular gas dynamics. And perfectly, this is aligned with NO gas rather than NO2 gas. But accidentally, we were able to detect this NO gas, and at the same time, we have two sensors with complete NO ppb and ppm levels of NO2 sensor. And later on, we combined this with a dual sensor, means the same material will be utilized for developing two sensors at two different levels of sensitivity. One is in ppb and one is at ppm for NO2 and NO. And again, with increase in research potential on development of graphene, we started to develop this by using Hammers method. But unfortunately, we couldn't get due to inert atmosphere, lack of inert atmosphere. We ended up in graphene oxide material. But there we had some industry problems. There they want to measure formaldehyde. So we used graphene material. Instead of graphene material, we used the graphene oxide material for developing formaldehyde into a gas sensor. It's a volatile material converted into gas and then carefully studied for gas sensing for a liquid. So the response also looks very good, and we have published this in 2-3 journals with important enhancement in our studies. And then after this, we went into nano hybrids. Instead of preparing these hybrids, which is taking 1 to 2 days, but we want to prepare these hybrids using microwave techniques. Same thing for NO gas, but with microwave technique, we were able to develop these hybrids within 5 to 6 seconds. And same thing have been studies and produced in Sensors and Actuators journal for these hybrids. Similar to that, we also have produced so many other hybrids for NO gas, CO gas, CO2 gas, dual gases, and very high temperature for military purposes, CO and NO2 sensor combined in one as a wearable sensor, which is typically located right next to your ear, within the collar of your soldier's uniform, so that you will be able to hear the alarm without having any quantification methods. That is one specific commercial product that we have developed. We also have developed for a metrological purpose, ETOH, ethanol sensor, where we have used two metal oxide, dual metal oxides, where the heterojunction of this solid state material have been utilized for detecting very, very low levels. Initially, we got 250 ppm. Further enhancements, it has been proved that it went down to 100 ppb levels, which is one of the important metrological device with this particular, with a shelf life of 3 to 4 months. And this is perfectly suited for handheld devices. And another nanohybrid which we prepared from HPMC, hydroxypropyl methyl cellulose, and TEOS nanohybrids, also using the same microwave methods. And with this, we have developed for anesthetics, sevoflurane, which is an anesthetic. This is a very, very primitive work where we probed a conductivity meter for sensing this anesthetics, where earlier it is being studied by using hyphenated techniques like FT-NMR. Each one is going to cost 1.25 to 2 crores. And with this 1,000 rupee sensor, we were able to detect different sevoflurane concentration with this particular experimental prototype. And once we have developed this, government has asked us to develop a wireless sensor, and further this has been improved. All these ups and downs have been removed by enhancing this particular material, and also at the same time we have studied the interference of this particular thing. And typically using a very high resolution FTIR, we were able to develop our own simple setup, and this particular FTIR matches with this high-end model, which is this particular high-end gas analysis ABM bromine with 0.001 centimeter inverse resolution is going to cost around close to 2 crores. This particular sensitivity has been obtained, and this is one of the officially commercially available sensors compared with our thing. And since it has been asked with to develop a wireless sensor to specifically induce or introduce this into hospitals at different levels, so that everything will be coming to the ground level, we converted this sensing scheme into receiving sector and a transmitting sector. Both have been connected by a wireless sensor. So initially this was with 25 meters, the distance between the sensing unit and the receiving unit. Slowly it has been improved by varying the electronics and varying this sensitivity of this particular chemical setup. We were able to retrieve very highly precise gas dynamics, and this is also published in Sensors and Actuators. And finally, once converting all these things into sensors into wireless sensors with the help of some electronic students, we were given additional thing for biomolecules, epinephrine. This is a complex molecule. It has so many advantages and disadvantages, but this, after 2 years of work, it has been accepted with a very good results, combining cobalt oxide and BiPO4 nano architectonic materials. And this was very recently published in Journal of Nanoscience and Technology in 2020. And earlier they are using HPLC MS, hyphenated techniques, fluid fluorescence, capillary electroporation, very tedious and simple method where you can go up to zeptomole concentration, which means 10 to the power minus 21, and other tedious electrochemical analysis. What we have developed is a simple method, electrochemical, changing in the electrodes, and then we were able to study the interference, and typically the material characteristics have been studied, and we were able to detect up to 55 millimolar of epinephrine in January 2020, and this has been published. And this 55 nanomolar is not that competing for the doctors, but they want to have enhanced sensors. So we developed another material, PT, platinum doped tin oxide material, as a core shell nanocomposite, so that the same epinephrine using this particular materials we were able to detect. We were able to study this core shell nanocomposites, and typically we went up to 13.5 micromolar concentrations. Earlier it was 55 micromolar. Now we have come down to 13.5 micromolar, which is evidently required for studying the disease. And we also studied different interferences, and ours is one of the best. And this has been published in Journal of Chinese Chemical Society after a lot of debate over a period of 3 months. But finally, this has been accepted to study. With this and so many other studies that we have done, we were given by WHO levosimendan, which is toxic material which signals so many brain-related signals, and it also obstructs so many things. And tetramethyl ammonium hydroxychloride, TMAH, which is also very corrosive and always prone for headaches and creating different brain signals, so that you will be unable to think in a particular direction. So these are the two things that we are trying to study. Soon we'll come up with something either with a polymer composite or electrochemical sensing, which will soon, once it is stabilized, it will be published. And to enhance further, we are trying to, for example, this is a typical CNT, and also with multi-wall or single wall, we are typically trying to cut this. Once you cut this, your enhancement and signal is going to be 10%. So why do we want to waste it? So we typically gave a acetic acid treatment for 1 day, and then we were able to cut the heads of the multiple CNTs and enhance. This is the typical picture where we use modified multiple CNTs to detect or sense, enhance by 10% the signal of our requirement. So in this way, we are trying to modify physically, chemically, functionalize them, and so many other things. And finally, this is a list of things that what we have done. These are the things what we got from WHO for develop sensor. We were able to develop up to 7. Rest are still uh, under work. And with this, our group was been in one of the top 5, which GE company in USA made the survey, and at the same time we also got 13 more chemicals for developing different types of chip-based chemical sensor, either wireless or wired sensors. The idea is to make it economical and sensible so that it will be able to detect at a very, very low levels. And we have developed ethylene sensor using TiO2. This is also costing around 200 rupees, a typical sensor. Using this particular thing, we entered into medical sector, and before entering into the medical sector with this ethylene gas sensor, so many other things have come up. But even in 2020, there is one ethylene gas sensor, but the sensitivity is only 0.1 ppm. But with this, with the previous sensor, it is going to be around 150 ppb or so. So our particular sensor is much more useful than existing complicated materials. This was in 2003, and this was in 2020. And they also have different types of zinc oxide ultra thin sensors for fast purpose, but the detection levels are not that very low for toxic NO2 gas compared to our previous sensors. As I said, with the ethylene gas inspection, we converted the entire thing as a breath analysis device where we want to calculate or estimate acetyl coenzyme A in our breath, so or acetone in the breath. So typically we have a TiO2 nanowires integrated, put them as an array, and then produced or scattered on the chip. And with this, we have done mixed signal circuit design and process integration into a device. And finally, we ended up a device, which is a handheld device with the cooperation from Canada, Taiwan, and 2 universities from Canada and 4 universities from Taiwan. And this is a $28 million project. And this has been successfully completed. And then the same thing is being implemented to integrate biologics where the donor equilibrium is being interrupted. That has to be set. So people are working. This is the typical micrograph of this particular rat brain where simple experiments are being done. And now the concentration is on wearable simple type of sensors, either to the body, energy enhancement, or energy alarming, or gas alarming devices. All these things are being done. People have stopped working on metal oxides, but they are converting that knowledge into graphene composites, reduced graphene oxides, and so many other purposes as wearable devices, so simple devices. So we have so many flexible implantable devices which we are working as energy harvesting and toxic gas sensing for healthcare, fitness, automotive, human interface, as wearable electronics, and even for the security purpose. And also, people are also going into the next level, which we are not working especially on this skin-inspired devices, because we are typically working on graphene-based wearable devices where graphite is being developed and converted into a pencil where you can draw the particular circuit using the graphite pencil on your skin so that it becomes a device on its own. So that means you have complete flexibility. You can create your own circuit on your skin, connect them into bits and pieces so that you will be able to analyze for so many other things. These are some of the things that one of the members of our groups are working to develop wearable health monitors instead of going to a healthcare center. And also there are so many other things for EEG, ECG, sweating, signal, and optometries, and angioplasty for any blockades, Just by measuring the flow rates, you can tell where the blockade, and so many other things, the heat that is being generated, and energy harvesting devices once you move, just like your watches, automatic watches. Once you move the hand, it generates its own energy. So that these things are going to appear in the near future. We also into different materials for sensing or detecting the signals. Typically, for as a meta material for defense purpose, we worked on two different types of materials. One is electromagnetic shielding, and the one is a microwave absorber, and the other two graphene related as sensors, as antennas. And you can also employ this in stress responding once you connect these with your telephone by measuring biotic stress or abiotic stress, which are absolutely responsible for massive loss in agriculture production. We are employing these sensors into the next level in agriculture, because in the world, agriculture output is going to be, as per the index, the lowest in the world is in India. And some of the developed countries like uh, Western world, they're tenfold superior than our productivity. Even the developing countries like Sri Lanka, Bangladesh, Vietnam, all those are higher in our indices. So these type of sensors are being implemented, M sensors in agriculture, so that the yield can be increased. So coming to conclusions, there are different types of sensors, CO sensors, NO sensors, and you can integrate them, further functionalize them, and you can utilize that for a very particular purpose which is required for your field by assembly and by optimizing these things. And at the same time, one has to be very, very careful, because of these materials are highly toxic, and you should make the safety into note of this particular thing. So cleaner, greener world is much better. Using this nanomaterial for sensor, it can be better served. And some of the references for you, if it is required. And at the same time, I try to thank the management of GITAM for giving me this opportunity, and students who are responsible for all this data, and my colleagues and my collaborators. Thank you one and all. If you have any questions, please do. Thank you.
Now
I think we are on time.
Yeah, yes. Now I request Dr. Anima Tadichi, Madam, Chair of afternoon session, to give the remarks.
Good afternoon, everyone, and good afternoon, Mr. Dr. Murthy Chavali. It was indeed a very good
Madam, Anima Madam, your audio is a bit.
experience was instantly evident in your presence.
Madam, your voice
Hello,
is not
can you hear me?
audible. Now it is clear.
Hello.
Madam,
Madam,
now it is audible. Again, you proceed with
please
the
repeat,
same question,
madam.
madam. Please repeat.
Yeah, sure. So I thank Professor Murthy for his wonderful lecture on materials for sensing. Your vast experience was instantly evident in your presentation, and the translational research in generating plethora of key technologies ranging from environment to electrocatalytic applications and the photonic applications, wearable devices for integrating biology and health aspects. So your work on, you have also highlighted in your talk that how we convert an ordinary office into smart office for, sensing the ambient temperature, humidity, shade control, etc. So his concept also highlighted that it is not important to miniaturize and technology, but the technology should also be precise, stable, reproducible, inexpensive, and robust, and it should be applicable in different arenas as you call it, as smart applications. So
That's
your
right.
work on sensing of carbon monoxide and different gases, nitric oxide, using indium and tungsten materials, graphene oxide, and organic inorganic hybrids really are worth mentioning during your presentation. Also, your work on humidity sensors and cost-effective sensing and commercialization of medical application of anesthetics. And I must congratulate Dr. Murthy for being in top 5 group for sensing anesthetics as recognized by WHO. Hearty congratulations to you, sir, for this wonderful research and bringing the technology and miniaturizing the technology for the benefit of the society. And now I
Thank you.
request, I hand over to Dr. Ratnamala for releasing the appreciation certificate, and before that to Professor Venkat Ratnam for any question and answer sessions. Thank you, Professor Murthy. It
Thank you.
was indeed a pleasure to listen to you.
Thank you. Thank you.
So, thank you, Anima Dadichi ma'am. And Murthy sir, a few questions from audience side. One question from Dr. Ramesh is carbon materials are in general toxic in the nature, and
That's
how
right.
they fit to be used for miniatured biosensors.
Miniature biosensors. Most of the biosensors are going to be replaced where they have used CNTs, multi-volt CNTs, because of the toxicity.
Okay.
Now they are moving into functionalized graphene area where the toxicity is being limited, because they are going to be in the form of sheets.
Okay.
These sheets are going to be less toxic compared to the earlier materials like fullerenes, CNTs, SWCNT. So the toxicity is not going to come up, but still there will be a little bit of toxicity, and that is going to be replaced by functionalizing for enhancement and reducing the toxicity using graphene nanosheets.
Okay. One more question, sir, from audience side. Vinod M is a research scholar. Sir, all those sensors which you have showed in your slides are directly mounted with polymer. But how this is possible? By molding or any PCBs like or any flexible substrates?
No, not everything is polymer based. We have metal oxides, dual metal oxides, where we mix this with TEOS or a binder. And in case of polymers, we develop the polymerization on the chip itself. So we call it as UV induced photopolymerization. So we take the monomer, polymerize on the chip. So it is in situ and it is triggered by UV. So our group is the first group to develop this UV induced photopolymerization on chip.
Okay. So one more
and this is directly monitored. It's crude way, but still I can share it with you people. We do this thing in a UV spectrophotometer where the chamber is there for analysis or taking a UV spectrum. We replace that one, we keep this one, and we study the entire polymerization process, how the peak is shifting.
Okay. So one more question, sir, from Raju. He is also research scholar. What type of polymers are used in the fabrication of electrochemical sensors?
Oh, there are huge numbers. One, we go by expense. If it is highly expensive, we don't go into that because we are all Indians. We always look into the low cost material. And at the same time, we try to get those characters into our low cost material by inducing some other dopants. So if you just name, there are N number. If you take photoactive materials, which is specifically used for electronic devices, there are around 50 to 75 materials which we don't use in India, just because of it is expensive.
Okay. Last one more, sir. He is interacting with Janardhan. You please.
Janardhan, this is Professor Venkatnath.
Yes, sir. Go ahead. Good to see you.
Yeah, Murthy garu, how are you?
Fine, fine, fine.
Okay, first of all, I'm so thankful to Murthy Garu, okay, for taking his time and sharing with his knowledge with our participants. Okay, I would like to share few things about Dr. Murthy Garu. So Murthy Garu and myself worked in one of the deemed to be university for a good time, almost 1 decade. And SAR is having an excellent research background, and his I10 index is 78, and then he is a mission of research publications. When we used to work with him earlier, we used to say that whenever he just shake the hand, we used to say that 2 or 3 SCA papers will come. Okay, so likewise, that's why he is able to get good number of citations and a very good high H index and I10 index around 78. That itself shows very good research output from Murthy Chawali Garu. So Murthy Chawali Garu, anyhow, any other member, okay, always they give information about their research work. Okay, our request, we would like to share one more thing. Okay, in our GITAM Bengaluru campus also, a good number of the faculty members are working in this materials area. And there are 2 to 3 groups are there. One group is there led by Dr. Manjunath Garu and one more Srilakshmi Madam, and then Dr. Chandrababu Naidu. Like that, different groups are working. So out of all these groups, Dr. Manjunath earlier he used to work in the energy sector. Now his team along with other members, they are also working in the sensors. So I think their okay, if you accept, okay, if you accept, they will collaborate with you in the sensor field also, because recently they have entered into the sensor field and published few papers also.
No problem at all. Anything for my good friend Venkatnath.
Okay. First of all, we are so thankful to you that you accepted our request. Okay, I would like to share one more point about Dr. Murthy Garu. Okay, generally those who do the research, okay, generally they won't much interact with other members, and then they feel that they are so high, and they keep themselves away. But Murthy Chawali Garu is entirely different. And though he is having so many number of publications with a high impact factor and a high H index and I index, he used to interact with even the junior most research scholar and faculty member also. And the main one more point I want to share with all the members. Okay, he is instrumental in establishing the research laboratories. That is his greatness. So SAR established almost 4 to 5 nano technology related laboratories, and one of the previous organization where we worked together. Okay, now I would like to request Murthy Garu to share some of the facilities whatever are available in Tamil Nadu, Andhra and Karnataka, where the member, okay, any scholar is going to about to start their work, characterization purpose, where they can approach, because you are having very good rapport with a number of the these analyzing instruments and their organizations. Please, sir.
Okay, if you're really looking at 2 different scenarios, one is paid services, the second one is fast services. In terms of paid services and fast services, I went with IITs. Definitely, I could not get proper result, and definitely it was not so fast. Usually, for example, some of the magnetic material studies, they took 3 months payment wise, but definitely it couldn't. Better is to have a collaboration without payment, and it should be fast. And I can give some of the list of laboratories. One is in MIT, Noida. The other one is NI University in Tamil Nadu, where I've developed a materials lab, synthesis lab, characterization lab, where they have almost every facility except SEM and magnetic studies. Rest everything they have. And in Vignan, for example, previous university, we have established a 4.5 crore laboratory where you have TGA, DSC, XRD, electrochemical studies, microscopic studies, SEM studies. And if you alter them a little bit, as an analytical chemist, if you can alter, you can get much more enhanced result. And you also have Amrita in Coimbatore, where in Trivandrum, where they are trying to help some of the students, and deemed university like Modi University, and one more in Jalgaon, where they have a nanotech research institute. And such research institute is going to come up with industries in Chennai, where they want to have something in the order of 100 crores only for nanotechnology. Once this is done, probably all the students can get with very, very little amount. Their studies can be done with highest precision and faster rate. And myself, my group, we are not paying anything and we are getting results, especially as you know, based on my travel to different countries. Our collaborators are there and we take out our materials, do the studies, and then come back. That's what I really do. Yeah, if you have any further thing, and in Andhra also, in 2 more labs are going to come up, where I am overlooking one of them. So if that comes, probably you can collaborate with that particular lab free of cost. From my side, it is open.
Okay, thank you, sir.
Okay.
Over to Venkatatnam, please.
Thank you, Murthy sir. And session is hand over to Ratnamala ma'am.
Okay.
Ma'am, may I release the appreciation certificate? Unmute yourself.
Okay, thank you. Okay, thank you, Professor Tekmurthy Chavali garu, for enlightening the presentation and good contribution to the scientific community. Now I request Dr. Venkatratnam to release the appreciation certificate to Professor Tekmurthy Chavali.
Okay, thank you.
Thank you. Over to Anima madam.
Okay then, Dr. Janardhan, thank you.
Thank you, sir.
Thank you, sir. Thank you very much, sir.
Venkatnadi
Thank
garu
you,
too.
Dr. Murthy. It was indeed a pleasure, and once again, hearty congratulations for your
Yeah,
work.
thank you.
I now welcome Dr. Paul Mogard to the E-ON 2020. Dr. Mogard is an associate professor in the University of North Carolina, United States. Dr. Paul Mogard is going to present his talk on mixed metal oxides for uses in the capture and conversion of solar energy. He will be discussing new routes to tuning the mixed metal oxides for efficient conversion of solar energy and solar-driven redox reactions. May I now request Dr. Paul Mogard to present his talk.
One second. Now,
I think.
one second. I'll.
Could I
Vikram
please
Bas-
request Dr. Basua to formally present Dr. Mogard to the attendees?
Yeah.
Sure. Thank you, Dr. Anima Sunil, for giving me the opportunity to introduce Dr. Paul Mogard. Dr. Paul Mogard works as an associate professor in the Department of Chemistry, North Carolina State University in Raleigh, North Carolina. He did his bachelor's BA in chemistry from William Jewell College, Missouri in 1995, and then he went on to do his doctorate in inorganic chemistry from Iowa State University, Iowa. Then he went on to do his postdoc in Northwestern University in Illinois in 2002. Dr. Mogard's research interests include solid synthesis using flux and hydrothermal methods, characterization of their crystalline structures and chemical compositions, and measurements of their catalytic as well as the photoelectrochemical properties for solar energy conversion. His current research focuses on the discovery and design of novel mixed metal semiconductors with ordered or semi-ordered crystalline structures as well as new carbon nitride phases and aerogel type materials. As of now, he has 101 journal publications, 4 patents, and 2 book chapters to his credit. Dr. Magad received various awards like the Thank a Teacher Award from North Carolina State University right from 2013 to 2019, the Scilog Award by Research Corporation for Science Advancement, the Career Award from the NSF, the National Science Foundation, the Beckman Young Investigator Award from Beckman Foundation, and Ralph Povey Junior Faculty Award from the Oak Ridge Associated Universities. Today, Dr. Paul Magad is here to give a talk on the mixed metal oxides for uses in the capture and conversion of solar energy. Dr. Magad, the screen is yours.
Thank you very much.
Sure.
Share the screen here, and good morning, everyone. Hopefully you all can see this now. I will enter it into presentation mode.
Yeah, it is visible.
So can you hear me fine?
Yeah, it is fine, Paul Magad.
Okay. Thank you for the excellent introduction, and it's my pleasure to present this Zoom lecture today on the topic of my research on mixed metal oxides for uses in the capture and conversion of solar energy. I've been at NC State for, let me see if I can enter, the past 18 years, and this has been my passion and my enthusiasm in research. Now, this has become quite a popular field, and for the capture and conversion of solar energy, there are 2 primary formats, at least to do this heterogeneously. One is in the form of metal oxide particles, which have been very efficient, at least in the ultraviolet. And how these systems work, how metal oxides work to convert sunlight into chemical fuels, is by their absorption through band gap irradiation, the creation of electron hole pairs within the particle, and then those electron hole pairs must be separated and then drive either water reduction and or water oxidation at their surfaces. In ultraviolet light, this can be very efficient in water, and groups like Domain and others have shown this, for example, for sodium tantalate, for strontium titanate. But their limitations are that they absorb only in the UV, and yet no visible light semiconductor has been found to do this efficiently. The other format that these work in is as a film. And so what you do is you take these particles, and rather than just dispersing them into an aqueous solution, you deposit and anneal them as a film, typically on something like FTO or some sort of transparent conducting oxide. And then in order to facilitate visible light absorption, little dyes are put onto the surface. And then those little molecular dyes can inject electrons and or holes into that film, which finds their way to the other electrode. And so on one electrode, you can drive water oxidation, and on the other electrode, you can drive water reduction. And this can be some reversible redox couple where what you're doing is you're generating electrical power, or you can be driving 2 redox couples that generates fuel, such as, again, water reduction and water oxidation. But the reason that you have to put the little molecular dyes onto the surface is that all of the stable semiconductors for this approach have a large band gap. And so what I've shown on the right here is the band gap structure, the valence band and the conduction band position for TiO2, and their energetic position with respect to the relevant redox couples. And in particular, water oxidation here in the light blue line, and then water reduction in the dark line here that's dashed. And so you can see when light is absorbed and an electron is excited from the valence band to the conduction band, you can drive just barely water reduction in TiO2. And conversely, you can drive water oxidation by holes that are generated in the valence band down here, and they can be driven much more energetically. So for example, water oxidation, at least in the UV, can be driven at high rates with these large band gap semiconductors. And what my group has been looking at for the past many years is how do you lower this band gap right? Such that you can appropriately position the valence band position right below this redox couple while also maintaining the conduction band position here, right above this redox couple, and then drive them very efficiently using sunlight as the electron is promoted from the valence band to the conduction band. And so we have to take a look at, to understand this, we have to take a look at what do the band energies look like at the electrolyte solid interface. And so here's just a simple schematic of how the valence band and the conduction band of an N-type semiconductor, what's called bend at the surfaces when the chemical potentials of the semiconductor equilibrate with the chemical potential of the electrolyte. And so you see that they're bent up as the electrons, right? If you have an N-type semiconductor, right, you have excess electrons doped in the material, and they empty out at the surfaces somewhat, and those bands bend. Now, this band bending is very important because this is in fact what drives the electron hole separation near the surfaces. And how far that band bending goes into the particle is also very important, because as light is shining on the material, you want to separate the electron hole pairs everywhere they're generated in the particle. And if that light is passing through the material, then you want the band bending to be occurring throughout the material, such that now you get the electron hole separation rather than the recombination in areas where the bands are not bent. So it's easily calculated here how far this band bending goes into a semiconductor, given the equation here, right? Space charge width, the width of the region from the surface to the interior of the particle, that this band bending occurs. And so it's a function of the dopant density, the dielectric constant, and the space charge height of the material. In other words, the difference in the chemical potential of the solid versus that for the redox couple for, say, water reduction. And so you can see here for different dielectric constants and for different space charge heights, right? The depth at which this band bending occurs can be from, say, 100 nanometers or less, all the way out to 1 micrometer, right? Depending upon the dielectric constant here and the space charge height. And so, for example, for ferroelectrics, which have very large dielectric constants, that space charge depth can go very deep. Now, for example, for TiO2 or sodium tantalate, we can compare these space charge widths to their absorption coefficients. In other words, the depth that light will penetrate into the particle before around 66, 67% of the photons are absorbed. Okay, and now this is also assuming that this is light with energy that is greater than the band gap. So for example, for TiO2, this is in the UV. And UV light in TiO2 will penetrate around 17 nanometers before around 2/3 of it is absorbed. Similarly, for sodium tantalate, because it has a lower dielectric constant, it will penetrate 167 nanometers on the order of before that much light is absorbed within the material. And so it's very important when you make these particles that you tune their sizes such that, you know, you have a space charge width that covers the full diameter of the particle. So if you look in the literature, for example, one of the most efficient semiconductors to drive water splitting is 1% lanthanum doped sodium tantalate. And the particle radius for this is around 0.1 to 0.25 micrometers, as you can see from the electron microscopy images. And the space charge width is about half of that, which is what you want, right? Because you'll have bending on all surfaces of the particle. And so you want the space charge width actually to be around a half of the particle diameter. And so there's a lot to do synthetically here to make these systems efficient in tuning the particle sizes, but as well the morphologies, because most solid state structures are anisotropic, meaning that when you excite electrons within them, right, their mobilities in different directions are going to be, right, higher in some directions, crystallographic directions, lower in other crystallographic directions. For example, if you have a layered material versus a three-dimensional material. So one of the methods that we use as an alternative to the simple solid state method, which involves simple grinding and heating of the materials at high temperatures, we use molten salt fluxes. And molten salt fluxes help with the solubility of oxides to dissolve them, right? And then to recrystallize them into different morphologies and different sizes, right? Depending upon their concentration within the flux, as well as the type of flux. You can change their sizes, you can change their morphologies. And so this is a very suitable, very appropriate technique to then look at how the photocatalytic efficiency for water splitting changes when you make them with different particle sizes and morphologies. And so that's, for example, one of the things that my group does. And so here's one recent example that we reported, sodium niobate, which has a band gap size of around 3.5 EV. And you can see in the SEM images on the left, we have made sodium niobate by a solid state approach, which has very irregular morphologies, very large sizes. And then we've made it using a sodium sulfate flux, where we've mixed in a sodium sulfate in a 1-to-1 or a 10-to-1 ratio, together with the reactant sodium carbonate and niobium oxides. And we see particle shapes which expose the 110 crystalline facets of sodium niobate versus the metal halide fluxes, such as sodium fluoride, sodium chloride, sodium bromide, where you can see predominantly cubic morphologies within each of the products here, going up in size from sodium chloride to sodium bromide, because the solubility of the sodium niobate is going down as you go from fluoride to chloride to bromide as fluxes. So this is a very nice tuning that you can do synthetically, and then measure the photocatalytic activity for hydrogen production when you disperse these into a solution. So in this on the right diagram here, what I've shown is the gas production, specifically molecular hydrogen versus time, for the products that we've obtained using the different fluxes. You can see the very highest activity is for when we have used the sodium sulfate flux to expose the 110 crystalline facets. Okay, versus we have much lower activities for the sodium halide fluxes. And so this comes down to the point that it's not just particle size, but as well the surfaces that have a prominent effect many times in how active this material is right at the surface. Just a few more examples from flux synthesis approach here. One is lead titanate, which has a relatively high dielectric constant. You can make it in a lead oxide flux, and you can have very large cubic shaped particles. And as well, if you use a sodium chloride flux, you can make much smaller particles, more in the nanometer size scale. And if you compare the activities for oxygen evolution and for hydrogen evolution, surprisingly, the much larger particles are more active, because in these cases, you calculate the space charge width at the surfaces here. And they're actually quite large, on the order of several micrometers for lead titanate. And so the larger particles support that deeper space charge width, whereas it vanishes for the much smaller particles here. Other prominent examples which could be discussed, sodium calcium niobate with a layered structure. You can make it in a rod-like format or a layered type format. And in this case here, you don't have a 3-dimensional structure, you have a 2-dimensional layered structure. And so by making the rod-shaped morphologies, you shorten the path length that the carriers have to reach the surface. Whereas in the layered type structures here, because the carriers are restricted to the plane of those layers, it is a much longer path length to get to the surfaces and to drive those catalytic reactions. So in this case, the below case with a layered structure is the example where if you shorten the path length to reach the surface, you get a much higher activity. Okay. Now let's talk about why that occurs in metal oxides. And I just briefly want to go into the fundamentals of the structure and bonding within these materials to understand why carriers would have high mobilities in some directions and not high mobilities in others. And then as well, it gives some insight as to how to tune the band gaps of these materials. And so I've shown you a simple electronic structure diagram here, a band structure. In this case, I've shown it running from X to gamma. And on the left, I'm showing you a simple TiO6 octahedron. And then on the right, I'm showing you an extended chain of TiO6 octahedron. And then now let's just very briefly go through what those crystal orbitals must look like as you take a metal oxide unit and extend it in 1D. And then this will apply to 3D as well. So I have the simple molecular orbital diagram of the frontier energy levels for a TiO6 octahedron here. And the band gap, or in this case, the HOMO-LUMO splitting, right, is determined by the non-bonding oxygen p orbitals here in the C2U and then the pi star unfilled levels of the d orbitals on titanium here, right? The d, y, z, x, z, and x, y. And that splitting determines its gap, okay? Now, when you extend it into 1D, what happens is you have to consider the overlap between the neighboring units. And at the x point in K space, what happens between the neighboring units is that you see that they're out of phase here. Okay, and so one d orbital is one phase, and then the next d orbital has switched the sign of the phase of the orbital here. And so they can overlap in an anti-bonding fashion. And so at the x point of the band structure, the d orbitals are pi anti-bonding. Now, as you go from x to gamma, what happens though is that the nodes between the orbitals decrease, such that when you reach the gamma point, right, there is no node here between the d orbitals, and they stay the same phase, going from one titanium to the next titanium. And now at the gamma point in K space, as you can see here, the p orbital does not have the appropriate symmetry to interact with either of the d orbitals. And so that becomes, in fact, it becomes a node, right? There's no interaction between that oxygen P and the titanium D. And so that lowers the band here and makes the crystal orbital non-bonding at this point in K space. And so as we go from X to gamma in the band structure, the DXZ and the DYZ run down in energy. And this dispersion is very important. When you have an electronic structure, right, like this, which shows a large band dispersion, that leads to high mobility of carriers in that direction of the crystalline structure. So it's really important that you see this band dispersion, right, and have a high band dispersion if you're going to have a high carrier mobility in your material, right, and so that they can reach the surfaces and drive that catalytic reaction before they recombine with the opposite carrier charge. And conversely, the band structure down in the filled levels for the oxygen orbitals, right, the highest energy levels remain the non-bonding energy levels. Okay, and so here, for example, this would be the crystal orbital at the X point in K space, as I described. This would be the crystal orbital at the gamma point in K space, as I described. You see now that there are nodes, and the difference in energy between this crystal orbital and this crystal orbital is the extent of the interaction between the p orbital here and the d orbital here. Okay, whereas the oxygen levels, they remain fairly constant at the top, right? And so that highest occupied orbital within your electronic structure in the valence band is always predominated by non-bonding oxygen orbitals. And so it's very hard to move this up and down in energy to lower the band gap. It's very easy by changing transition metals to change the position of the conduction band here. You can take a look at this by DFT calculations and you find consistent results as well. And so here I'm plotting energy versus a K space for TiO2, its anatase polymorph. And in particular, I'm showing you the conduction band. And so this G is the gamma point. And as I described, at the gamma point in K space, as we see as the result of DFT calculations, we have titanium d orbitals that are non-bonding, right? There's no overlap between the electron density on the titanium here and any electron density on the oxygen. But then as you go away from the gamma point in K space, this band disperses up very fast in energy, right? The effective mass of an electron in that band is proportional to the rate, right? The partial differential, second partial differential of energy with respect to K and K space here, right? So that the more dispersed that band is, right, the lower the effective mass. That's really great for having high carrier mobility. So the upper part of the band here, I've plotted out the electron density, and you can see that there's a significant overlap now of the titanium electron density in blue, and then the oxygen electron density in this green shaded region. You can see it's shaped like a p orbital, right? Just as what you would expect. And so this is one of the reasons why the carrier mobility, right, in TiO2 is so great, and it's actually has a great mobility for the carriers to reach the surface and drive water oxidation or water reduction. In this case, it would be water reduction, right? Because this is the conduction band. Similarly, I could have shown the valence band as well. So here's a summary for TiO2. That's kind of gives an important lesson. If you're going to try to tune the electronic structure of these materials, how you can do it, right, is by shifting the conduction band up and down. but you really have no opportunity to shift to the valence band up and down. Okay, so what's important? The identity of the early transition metal cation is important, right? It determines the energy of the conduction band. But then as well, the dimensionality of that crystalline oxide network is also important. You're only going to have a high mobility in the directions of high conductivity or extended conductivity of that network. And what's more, if you want to close this gap down, right? Close it down from being absorbing in the ultraviolet region to absorbing in the visible region, you really have no opportunity to do that without adding now a third element, right? Something that can come in and insert filled energy levels here and shorten the gap between this region of the forbidden region and the conduction band here. Yeah. Let me move through this a little bit more quickly now. Here's another example where you have a layer type structure, D. N. Jacobson phase, rubidium, lanthanum, niobate, and it's constructed of NB06 octahedra that condense together into a 2D layer with rubidium separating those layers. And as I described earlier, electron mobility is going to be the highest within those layers. So as you shine light on these particles, which crystallize out from flux synthesis as platelets here, right, you can basically image where the reactions are taking place by photodepositing metallic platinum onto the surfaces. And so platinum salt, platinum 2+ is easily reduced to platinum metal by any electrons, right, with a sufficient reduction potential. So when you shine light on these particles in the presence of a platinum salt and an aqueous solution, you see those platinum islands are depositing in little rings that occur at the surface of the particle, right? Highlighting the fact that as your light is hitting the material and exciting the electrons, those electrons have mobility within the plane until they hit a little step edge, right? Until they reach that outer edge where they can drive that surface reaction. And so similarly, when you're driving water reduction, for example, to hydrogen, right? The more step edges you have, the higher the rate, right? And this is basically where the reaction is occurring. So very frequently in the literature, you will see that this is a nice way to image where water reduction is taking place. You can also image where water oxidation takes place by taking a lead 2+ salt in solution, shining light on your material, suspended in that aqueous solution, and that lead 2+ will precipitate out and deposit as lead 4+, as lead dioxide at the sites where water oxidation would be taking place. But in this case, right, for example, lead oxidation would be taking place, just to give an idea of how to image it. Okay, so let me come to the point of how we synthesize materials, not just with the right morphologies and sizes, but as well now with the right band gap. And I've shown here, right, several well-known metal oxides and their energetic band positions, or band edges, I should say, for the conduction end as well for the valence band here. And they all have very large band gap sizes. For example, zinc oxide, strontium titanate, sodium tantalate. You notice that that conduction band edge, right, varies a lot. It needs to stay above that proton reduction redox couple, right? So for example, tungsten trioxide falls just a little below it, right? But you can, vary the early transition metal, right, and vary that position. What's not changing here, however, is that oxygen valence band edge. And if you want to have a highly efficient solar energy converter to make chemical fuels from sunlight, you want a band gap that is not as big as 3 to 4, right? You want, to reach the maximum efficiency of 33%, you need an optimal band gap of around, well, for absorbing the light, right? Because it's a balance of carrier thermalization as well as having a small enough band gap, right? There's an optimum region of around 1.2 EV, right? But you need to add in the overpotentials to drive those half reactions at the surface. So an optimal band gap is typically estimated to be around 1.6 or 2. And so to drive this research in the direction of more efficient metal oxides for these reactions, our hypothesis was at the very beginning when I started here, including transition metals with filled D10 and D10S2 orbitals, such as silver plus, lead 2+, tin 2+, who would add in those filled energy levels here within the electronic structure and shorten the gap. Now, of course, we have to keep the connectivity of the early transition metal as well. And so what we're shooting for is a metal oxide structure, which has extended connectivity of both these candidates, right, silver, lead, tin, combined with the early transition metals here, right, and position them appropriately such that there'll be high carrier mobility in both of those networks, and they can absorb a large fraction of the sunlight, okay? But how do you do this? So this is a synthetic problem, because many of the compounds you would make with these transition metals here and main group metals, cations here, have such a small band gap when combined with niobium, tantalum, and titanium that they're often not that stable at high temperatures. Okay. So the candidate system that we looked at in the beginning was this layered phase, which has pentagonal bipyramidal layers for tantalum. And so the composition is Na2Ta4O11. Its band gap size is around 4.2 eV, and it has this trigonal space group here. Okay. And what you have are these pentagonal bipyramidal layers, and these are connected together by isolated octahedra between them. And so, for example, I've shown you one basic unit here of the connection of one layer and the next of that octahedra. Okay, and the reason we chose this is that it's pseudo two-dimensional, and in this structure we can exchange out that sodium, right, in the chemical formula Na2Ta4O11 with all of those other main group and late transition metal cations I showed you, using our flux synthesis conditions. So we can make this material first by flux or a solid state approach, and then use what's known as a flux exchange to replace the copper or the sodium with copper, for example. So here's a UV vis spectrum when you do that of replacing sodium 1+ with copper 1+. Copper 1+ therefore is D10, and it has relatively high energy orbitals. You take the UV vis diffuse reflectance of this as a function of the copper content, and you can see the edge, which begins at around 4 eV, right, which is the band gap for sodium tantalate without any copper in it. But more and more copper in it, you can see it now it edges out some, right? And at around 10% of substitution, a fully formed band is occurring. And so a new edge comes in, and it's in the visible region. And when we put the maximum amount of copper into it, we get the smallest band gap size of around 2.65 eV. And you can see in the electronic structure calculations by DFT methods that the d orbitals form the conduction band. And so you can see here are the tantalum orbitals with the electron density shown in red. And then now here are the copper orbitals with the electron density shown in blue. And these constitute the valence band, whereas these constitute the conduction band. Okay. So you can make these all the way up to 100% copper within the material, with, again, pentagonal bipyramidal layers that are either single pyramidal layers or double pyramidal layers, right? In this case, this composition leads to n equal to 2 strictly double layers. This composition of 5, 11, 30, right? Still copper is 1+, leads to an n of 1.5, which is a mixture of single and double layers of these pentagonal bipyramids. And again, these are all visible light. We took each of these because we really, when we suspended them in solution, we didn't see much activity. We took these as particles, and you can anneal them on FTO slides and create photoelectrodes from them. And so this is what we did. So we can apply potential and see if upon irradiation, if we have N-type or P-type semiconducting behavior, and if photocurrents are very high. So this is what we did. And this is basically how our system functions, right? And so we have a Teflon container, we have a working electrode, we have a reference electrode, which is SCE, and then we irradiate the film. Okay, this is different. This is not a suspended particle in solution. This is now a film, so that we only have to drive 1/2 reaction on the surfaces here. And I've shown it by comparison to P-type copper oxide here, where copper is 1+ as well. In this case, the bands are bending down because it's a P-type semiconductor rather than N-type. And this is the same behavior we see for all of our copper 1+ semiconductors. Upon irradiation, what we're going to see is that the electron holes are separated at the surface, driving proton reduction to molecular hydrogen, and then the opposite carrier making itself to the counter electrode and driving water oxidation. Okay. This is the case for a P-type semiconductor. The other thing that this measurement allows you to do is to determine the conduction band and valence band positions using Mott-Schottky measurements, which we have done, right? And so in all of the diagrams that I'll show you later on, right, I'll show you the positions of both of those energetic bands. And I won't go through the details here unless there are questions concerning it. Okay, and so again, you set these up as films, you irradiate them in an electrolyte solution, and you measure the photocurrents. And so here I've shown you two plots. One where we've taken the film, we've annealed it, and then we've heated it to 350 to oxidize it some, or we've taken that same film and heated it to 550 to oxidize it some. And we swept the potential under chopped light. And so as you see this curve going to the right here, right, we're sweeping the applied bias of that film negative, and we're chopping the light on and off. So when the light is irradiant on it, right, we see a photocurrent. And when the light is off, no photocurrent. And so if we have a current density we can measure as milliamps per centimeter squared for surface area of the film. We see a current density of around 1.5. Okay. For N-type oxides, right, the most efficient ones, which have efficiencies of 10, 20%, right, current densities, you want to get up to around 20 to 25 milliamps per centimeter squared. For P-type oxides, which is what these are, it is very difficult to get high current densities like this. And so this was surprising and nice for us, right? The films at 350 showed a fairly high photocurrent, and as well, the films at 550 showed a high photocurrent. What I haven't showed you, though, is the fact that if you don't heat these films at all in air, they have almost no photocurrent, which is strange for us, right? So we make the films, and it took us heating them in air to see a significant photocurrent, right? To see the significant activity. And so we looked very closely at the surfaces to see what was going on, right? What's responsible for this behavior? So here are SEM images of the, in this case, a 51130 composition, and where we've made it by flux synthesis. And the flux synthesis gives you nice, highly faceted crystals. And so you can see there's nothing on the surfaces. But when you heat them into air, at 350, you very easily notice these little islands building up on the surface, both on these outer edges of these hexagonal type platelets, and as well as any step edges during that crystal growth that, that's formed as well, the little particles that are forming. And now when you heat it to 550, those little particles are much more prominent. And so you can see them populating the edges of all these particles in significant amounts. They're not forming a connected network, mind you, right? They're forming little isolated islands at those edges. And somehow those are leading to the very high activity at the surfaces upon irradiation. You take a look at this by XPS, which we did. You can see what's happening at those surfaces is we have primarily, right, copper 1+ in the pure bulk material. And as you heat it to higher temperatures, right, you're oxidizing that copper 1 to copper 2. And so we see the satellite peaks appropriate for copper 2 coming out in the XPS. And right, in XPS is highly surface sensitive. So this is detecting at the surface a very large amount of copper 2 coming out as we heat it to higher temperatures. And so this is non-heated, and this is heated to 450. And so if you balance the reaction, right, copper 51130 is all copper 1+. And as you heat it, you're driving out copper oxide islands at the surface. And so there's an oxidation taking place there at the surface. And then as well, internally, right, the copper 1 is being oxidized to copper 2 as well. Okay, until eventually you heat it to too high of a temperature, and then it's a complete decomposition. Okay, and in this case, our photocurrents completely go away, right? And so the two temperatures I've shown you and their photocurrents, those were the highest ones that we could measure. Now we look at the crystalline structure, and we can say, yes, now we can understand how copper is coming out. Because if you take a look at the particle morphologies and how those pentagonal bipyramidal layers are oriented, within that network, right, between the pentagonal bipyramidal layers, you have the copper atoms, right? And they are located between the isolated TaO6 octahedron. And you can move them, right, from one site to the next with a very low activation barrier. And there are diffusion paths in all three crystallographic directions, or I should say within that plane, for copper to reach the surface and to be oxidized. Okay, and so even at 250, at 350, there's a high mobility of copper 1+. And in the presence of air, of course, you know, copper 1+ will oxidize to copper 2+. Okay. So this is what's happening at the surface. As we heat it up, that copper is being driven out, and copper 1+ is being oxidized to copper 2. And that, in fact, is what's making it a p-type semiconductor. You can do the same thing, though, not by oxidizing the particles, but by making the nanoparticles of copper 2+ oxide, and then just depositing them onto the surface. And so we've taken the same films, made nanoparticles of cupric oxide, and deposited onto the surface. And again, we see those very high photocurrents occurring, which tells us that they're critical for that activity, right? That our bare surfaces are not, or while that material can absorb the visible light, the bare surfaces are not catalytically active by themselves. We've done the same thing with many other copper 1+ oxides. And in fact, copper 1+ semiconductors, this is a highly active field, with a lot of people working on the telephosphites, crystalline structures with copper 1+ in them, and many others. And so here's just one more example of the different crystalline structure with the 138 composition now with niobium oxide rather than tantalum. And the reason we went to the niobium oxide is now we have a much smaller band gap because niobium d orbitals are much lower in energy. And so here's the crystalline structure of the 138 phase. And again, we can make it by flux synthesis and heat them in air. And you can see those particles, once you heat them in air, right, compared to the before you heated them, they look like they have chicken pox on them or smallpox or something, because those little islands come out at the surfaces, okay, which makes them highly active particles for a water reduction. We've imaged many of these, for example, using FIB to slice out small sections of them and picking them up and imaging them. And we can easily see we have little copper oxide islands at the surface. And for this one, for example, we have the 010 direction of the crystalline structure oriented above the material, above the substrate of the 138 phase. And then if you image the 138 phase, right, we have the 103 direction imaged here. And all of these we're taking on TEM. With compositional analysis, it's also highly apparent, right? So here we've deposited the platinum on top of it just to be able to pick it up off of the base, right, and to image it. And so this is something that was done within the electron microscope. And then we image the elemental composition for the copper oxide, these islands, right? So you can see they're all green, they're all copper with no niobium in them, right? No niobium in them, okay? And then below that copper oxide, we still have the 138 composition where you can see below it here, right? It's niobium, oxygen, and small amounts of much smaller amounts of copper. The other interesting thing that comes out of this we discovered upon careful inspection of the XPS is that within the oxygen peaks shown on the right here, okay, there's a binding energy appropriate for oxygen 2-. But then as well, at even higher binding energies, we see a peak emerging as you heat it from 25 to 450 to 550. We see peaks emerging that are appropriate for O- defects or the formation of peroxide at the surfaces, right? So oxygen itself appears to be being slightly oxidized, which was confusing for us because, you know, you would think it would just only be copper 2+ being oxidized, or copper 1+ being oxidized to copper 2. But given this evidence here, we took a closer look at the electronic structure to see what could be happening. And so within the structure of the 138 phase, right, we simulated it with full copper occupancy and no vacancies here, with 25% vacancies here, and then with 50% vacancies here. Okay? And at this, we have the valence band, and here the conduction band. And at the valence band edge, what you see emerging in the red peak here, and then here, and here, or the oxygen p orbitals. Okay? These p orbitals are getting higher and higher in energy as copper is removed. That's because as copper is removed in the structure, as shown in these images up here, right, is this copper and this copper is removed, those orbitals on copper would normally interact and push down the oxygen bonding orbitals and themselves be raised by their interaction with oxygen, right? And so you would have bonding and anti-bonding levels. But when that copper is removed, there's no more interaction to those oxygen p orbitals here. So as copper is removed, those p orbitals climb significantly in energy. And this is important because it actually leads to a mechanism of more efficient charge separation. Okay, because now wherever there's a copper vacancy, you have the highest oxygen orbitals in your diagram. And wherever you have copper still occurring in your material, not vacant, you have the lowest part of the conduction band. And so if you plot out the electron density of the material, okay, wherever there's copper, right, you have a very low part of the valence band, right? So I'm showing you the valence band, the top half EV of it in orange here, and the conduction band, right, the bottom half EV of it, blue here. When we introduce copper vacancies, right, the lowest part of that conduction band occurs up here. Wherever we have copper still present, that's right, that's the highest part of the valence band. And so there's this nice mechanism now of charge separation driven by the copper vacancies. And as you saw in the electron microscopy images, those copper vacancies are not just random, okay? They're segregated. They occur mainly at the surfaces. And so there's a significant difference in the chemical composition of copper at the surface versus copper in the bulk that drives the charge separation at that electrolyte solid interface, which is really important. Okay, so let me show you just the results of the Mott-Schottky measurements and the positions of the bands of each of these semiconductors versus the copper oxide that we know is at the surface. And so for the 51130 phase, it has a higher band gap. And so there's a large driving force of the electron to move from the conduction band of the 51130 to those surface islands. And the same thing for the 113 phase here, copper niobium, which I haven't had time to describe. In both of those cases, we see very high photocurrents, right, for a p-type oxide, such as shown here for the 113 phase. Very nice. But for something with a much smaller band gap, such as the 138 phase, there's a much smaller driving force between its conduction band and the conduction band of cupric oxide. So when we measure its photocurrents, they're typically very poor. Right? You see a very high dark current, and it's kind of unstable, and photocurrents are very low. Okay, so this is further evidence showing us that those islands at the surface are important to drive that charge separation. Now, I must go back here and make one further comment. And the comment is that copper oxide systems, especially 1+, are relatively unstable in solution. So these will photodegrade over time. And many other groups have looked at how you put protecting layers on their surfaces to make them highly stable and to maintain a very high efficiency. And this really hasn't been a direction that we've pursued in my group because of other competing groups that are pushing this direction very well. Rather, we've looked for alternative means of driving this charge separation without the copper oxide islands, and that could lead to higher stability. And in particular, what we've looked at are solid solutions. And so in solid solutions, what that is mixing onto one crystallographic site, two elements, okay? And so think of it this way. I described the 51130 phase before, okay? And in that case, it was all tantalum. You can make that same phase now with putting in more and more niobium on the tantalum site, such that the crystalline structure has a distribution of both tantalum and niobium on the same site. You may think, well, what could that do? Okay, and this was a very unusual situation that led to a surprising result, which I'll describe. Okay, so we chose this 51130 phase, and its crystalline structure I described earlier, pentagonal bipyramidal layers with copper between those layers. And here are its valence band and its conduction band positions. Okay. We chose it because the valence band position is appropriate to drive water oxidation. We want to lower the conduction band now down to here. We knew we could do that with niobium. So we did this. We made all of these, in this case, by a solid state approach, putting in from 0% to 40% niobium onto that site. And you see that in the UV vis diffuse reflectance, the band edge shifts into the visible, and we're absorbing a large fraction of the visible light now. And we're getting down to a band gap size that is getting nearly ideal, around 2 eV or so, with 40% niobium into it. Again, we made films of these and measured the photocurrents. And this time we measured them without heating them in air at all. And so in these cases, there's no copper oxide on the surface. What we see is we're putting more niobium into it. We're getting higher and higher photocurrents for this case, because we're absorbing a larger amount of the light. And as well, we're getting charge separation. We have to be, right? And the question would be why, right? This is unusual, because if this is a very disordered crystalline structure, you would think there would be a lot of trapping and disorder, and the carriers would not be able to reach the surfaces very efficiently, yet they do. If we do the reverse solid solution, though, we see no synergistic effect. In other words, if I take a copper niobate and I mix tantalum into it, I see no improvements in the photocurrent. In fact, they stay relatively constant no matter how much tantalum I put into it. Okay, that's the reverse solid solution. So let me explain why a solid solution in it, you could still observe this carrier movement throughout its network. And so we did electronic structure calculations again. And in this case, we have parts of the structure here in green, where I've put in extended networks of niobium, and another part of the structure where I inserted an isolated niobium, just to see where the states would emerge within the electronic structure here. And so I have here a densities of states plot of both the valence band and conduction band, and then the atomic orbital contributions to them. Okay, so the highest parts of the valence band, you see the predominant contributions are from copper. Now in the conduction band, we see contributions from both niobium at the lowest parts of that band, which is what we expect, and then tantalum from the highest parts of the band here. Okay, and so let's zoom in on this little image, this little part of the densities of states, and see what the contributions are from. Okay. So I've labeled the different regions of the conduction band here, 1 through 5. 1 at the lowest energy of the conduction band, 5 at the highest energy of the conduction band. And so I plot out the electron density contributions arising from this part of the conduction band. And that's the extended niobate network here, right? And so you can see the electron density in yellow. That is what's contributing to the lowest part of that conduction band. Now let's go to 2. We go to 2 and we start seeing contributions from the isolated niobium part of that network. We go to 3, right? Here's the electron density from region 3 in the conduction band. And now you see the electron density is spread out more from over both the isolated niobium as well as the extended niobate part of that network. And then 4 and then 5. And by the time we get up to this high energy of the conduction band, the electron density is spread out over that entire network, such that when you excite, right, when light excites an electron from the valence band to the conduction band, right, because there's multiple wavelengths are coming in, and so electrons are being excited from high energies to low energies in that conduction band. No matter where those electrons are excited to, they rapidly thermalize to the bottom of the conduction band. Yeah, so they rapidly thermalize to 1. So wherever those electrons are being excited to, they're going from 5 and then thermalizing very fast to 1. So those electrons are thermalizing to the extended parts of the network and not to the isolated parts of the network. They're not becoming trapped. The electrons are becoming delocalized, even though you've got a solid solution. Okay. So the states in the conduction band, right, from low to high in energy, go from the extended to the isolated niobate polyhedra, which is important, right? Because anytime you have a solid solution, you have a high amount of disorder, you need a mechanism that will delocalize those carriers onto the extended parts of it and keep them away from the isolated parts. But at what point, you may ask, at what point does there arise an extended connectivity within that network? And this has been worked out some time ago, especially by Broadbent and Hammersley, as you can find in this reference at the top. And the theory is called percolation theory. And you can use it to calculate statistically, randomly, at what point, when you mix two elements or more on one side, at what point does there become a connectivity of those sides from one end of the particle to the other, okay? So here are basically four diagrams. One with 10% niobium, 90% tantalum, where niobium is in white, tantalum is in red. And you can see it at this amount, randomly distributed, niobium is just isolated. You go up to 30%, you can see, well, there's a much higher connectivity, right? Here's four neobates connected together. Here's a much larger cluster connected together, but you haven't hit that threshold for there being extended connectivity from one end of the crystal to the next. Now you hit that threshold for a 2D connected network at 50%. So at 50%, now the neobates, which are distributed just randomly here, right? And this is just one random snapshot. They have a connectivity that are going to extend from one part of the particle to the next, such that when I excite an electron into that conduction band, there is a pathway for that electron to become delocalized and make it from the inside of the material to the surface to drive the reaction. And that's the threshold you have to reach for a solid solution to be highly active. And if you go up even higher than that amount, you have even greater amounts of connectivity, but then the driving force for that electron hole separation is less. And for reasons of time, I'm going to skip a little bit of this here, but you can go and read about percolation theory and the relevant literature. And the point at which you hit that percolation threshold, what it depends upon is the connectivity of the lattice, Z, okay? And then as well, the dimensionality of the lattice. So that connectivity, Z, times the percolation threshold is approximately the dimensionality of the lattice over the dimensionality minus 1. And it's easy to calculate for simple networks here, okay? So for example, for HCP type structure, which has a connectivity of 12, you hit that threshold at only 12% substitution, okay? Whereas for the diamond lattice, which has a connectivity of 4, you need to put in around 38.8% substitution before now you have a connectivity throughout that material, okay? So it takes, if you have a diamond structure, it takes a much higher amount of substitution to hit that threshold versus something with a much higher connectivity. Okay, and so we've looked at this for many of our materials, and we've kind of, in recent years, moving away from copper because of its stability problems, and it shifted more towards tin-containing systems that also result in very small band gaps. But they're very difficult to make because tin 2+ is kind of an unstable oxidation state. It oxidizes easily, it decomposes easily, and it's very hard to make. But luckily, all we have to do is put in enough tin to surpass that percolation threshold and to get the favorable electron hole separation and to drive these photocatalytic reactions. And so, for example, we did this in some of the networks, the 2,4,11 phases. We actually did a double solid solution where we mixed tantalum and niobium on one side and sodium and tin on the other using a flux exchange reaction. And we can shift the bands for both the conduction and the valence band to the visible region. For example, here are the valence band positions for different amounts of tin substitution, and here are the conduction band positions for different amounts of tantalum substitution. And we can bring the bands together systematically, bracketing the redox couples for water oxidation and water reduction, which now shows the power of this technique to tune the band gap. And then in a solid solution, right, have a nice driving force for electron hole separation. And I'll kind of skip through some of the details here just for reasons of time. But all of these were measured using Moss-Schottky analysis. And as well, the rates for example, molecular hydrogen production were also measured. And the rates for the molecular hydrogen production peak, for example, when you put around 30 to 35% of tin in over the sodium site here. And this matches very well with that calculated percolation threshold that I described for, in this case, the valence band. Same thing applies for the conduction band too. Okay. So this covers all of the topics that I wanted to present today. And I hope within my talk, you've seen the various facets of designing semiconductors such that you have to make the appropriate sizes of particles. You have to expose the appropriate crystalline facets and consider mobility of the carriers within the various networks of that material. And then as well, modify the band gap size to absorb in the visible region of the spectrum, okay? And this is a very, very challenging problem. And I've shown you some examples of using copper 1+ and tin 2+ to make small band gap semiconductors. In the case of copper 1, they were all p-type semiconductors, and they drove water reduction at the surface. In the case of tin 2+, these were all n-type semiconductors, and they drove water oxidation at the surface. We're still looking at many new tin 2+ oxides. That's a very promising system. And hopefully now you see in the form of solid solutions, right, this can drive charge separation. And not only that, and I haven't had time to discuss this, but you can make metastable phases using solid solutions. In other words, kinetically unstable phases can be stabilized using solid solutions because you have the multiple cations kinetically trapped onto their sites. So you can exchange in higher amounts of tin or higher amounts of copper, even beyond thermodynamic stability. And in the case of copper 1, how important the surfaces are, especially putting copper oxide onto the surfaces. I would like to acknowledge my former and current group members for all their contributions to the project. Here's my current group. It's relatively small in size, but highly productive. Magnus, Eric, and Sean. And then the group members that have worked in the past on this project, Doctors Nicole King, worked on the copper 1+ oxides, and Woltersdorf, Ian Sullivan, Prangya Sahu, and Brandon Zollner. And I'd like to acknowledge our facilities here at NC State, which are some of the top in the world, as well as my collaborations with various PIs here, Jacob Jones, Samuel Doherty, and Dr. Sean. And finally, I'd like to thank NC State and as well NSF for their strong support and funding of this research. And actually, lastly, I would like to thank you for the invitation to give a short talk about my research during this meeting. And so thank you.
Thank you, Dr. Paul.
Yes.
Dr. Paul, it was a wonderful talk. Very extensively explained about how we can exploit the properties of different materials by changing the temperature, by changing the metal and percentage of metal with which it is doped. So Dr. Paul has stepped up the intensity of the talk. He started with metal oxide and how to convert the solar radiation by deposition of these metal oxide materials and lowering the band gap for the certain redox reactions. He discussed about charge separation of metal oxide and how the space charge width can be exploited to increase the efficiency of conversion. And he also talked about the dielectric constant of materials for the separation of efficient metal oxide. He discussed about lanthanum doped sodium tantalate structures prepared by flux mediated synthesis and how the molten salt flux method is more efficient than the other methods for enhancing the photocatalytic activity of materials. He also discussed about how we can bring about variation in the property by changing the percentage of niobium and sodium calcium niobate oxide. He discussed about the band engineering by changing the different transition and post-transition metal cations and how we can change the configuration and higher energy balance band can be converted. Substitution of copper in the sodium tantalate oxide, and by substitution of copper, how we can change the photochemical activity of the material. He discussed about the characterization of these materials using different photochemical characterization method, and comparison of photocurrent and dark current, effect of temperature thereon, and variation of electron density with the metal vacancy. We also talked about how copper 1 can be stabilized by creating protective layering methods and how overall percentage efficiency can be increased. So indeed a very detailed talk, and I'm sure people who are working in the field of solar energy, especially creating metal oxides, they must have been benefited a lot by your talk. And many attendees probably are waiting to interact with you, Paul, and I don't want to make them wait any longer. Thank you very much for your talk in this E-ON 2020. I now hand over to Dr. Bikram for question and answer session. Dr. Bikram.
Thank you, Dr. Anima Sunil. Thank you very much. Dr. Magad, we do have a couple of questions for you. So there is a attendees by the name Sissy Abraham. The question is, like, what is the stability of the cuprous-based tantalum oxides?
Yes, this is a good question, because this is often a problem in the copper systems. Their stability at the surface has been an issue in the past. And so when they're unprotected, they're not active, right? But with the little copper oxide islands on them, they're active on the order of, I would say, only tens of minutes. To get a much longer stability, you need to coat them, which groups, for example, Gratzel have used. They've used many different coating techniques to extend their stability to days, right? This has not been our expertise per se, right? And so we've not gone in that direction. But always, when you have a scientific problem, you tackle that segment of the problem you are the expert on, right? And so we have stayed to tackling our specialty. And
I get what you're saying.
Yeah.
Thank you very much. And there are a couple of research scholars who would like to interact with you directly. So is that okay with you?
Yes, this is fine.
Yeah, sure. Off to Janardhan. Janardhan, please.
Okay, Mr. Sandesh. Mr. Sandesh, you unmute yourself.
Good evening, sir. Can you hear me?
Yeah, it is audible, Sandesh. You can pose your questions to Dr. Paul Mugat.
Thank you. Hello, Paul, sir.
Hello.
I have 3 questions to ask you, sir.
Yes, please.
The first question is, why most of the copper materials are used in photovoltaic films, and why not other materials?
So for the copper materials, they had not been very widely explored. So when we began our research here, only the cupric oxide or the cuprous oxide, only the simple ones had been explored. And we thought by making ternary oxides, where you take the copper and you combine it with niobium and you combine it with tantalum, the idea was this would be new, something never before explored, right? And so we focused on these systems with the idea that maybe this mixed metal oxide combination would give a higher stability to the copper surfaces. So we focused on this primarily. And of course, when we receive funding to do it, then that also focuses our efforts to the copper system. But they're not only important for solar energy, but they're also a synthetic challenge, right? And so we can drive the field of synthetic chemistry more by discovering new ways to make them that can then be applied to other metal oxides that have low stability.
Okay. And one more question, sir. And
yes.
What is the optimum dopant percentage required to show the photocatalytic activity?
I didn't hear the first part of the question. What is the optimum percentage of what?
Sir, actually, okay, I understand, Mr. Sandesh. Sir, he's asking what is the optimum dopant percentage is required to show best catalytic activity of any photovoltaic cell? That's all.
Yes, this is a good question as well, right? Because you saw the dopant percentage controls that space charge width. And as well, I mean, there's many things that impacts, and it depends on the material that you're specifically working with. So there's not a number that is one number for every material, right? It depends on each material, and I think you have to optimize it empirically at this point. Okay, and typically most materials are doped 10 to the 17th, 10 to the 18th per reciprocal centimeter squared, I believe, or cubed, I should say. So this is not one number, unfortunately. You have to optimize it for every material.
And last question, sir, and I don't know how related is that question, which I'm going to ask you. And is the material which you are making, like, is the flux which will coated on the solar cells?
Is the flux material, I'm sorry, what for the solar cell?
Okay, whatever the material you are synthesized up to now, you can directly coat on a solar cell. That's what his question.
Oh.
Is this a flux?
So in the flux technique, these are making freestanding particles. And so the flux technique we have not used to deposit them directly onto a substrate yet, right? Some techniques, though, for example, have been used to grow the material right from the substrate. So for example, this is at the frontiers of research. For example, you can use hydrothermal synthesis and grow directly from the surface the semiconductor, right? And we have not, our approach has been to make the particles by the flux and then to anneal them and center them as a film, right? But I think this is a great idea, that the next step should be, right, how do you take this technique and then grow it directly from the surface? Because then you have much better contact and better control over the film which grows, right?
Thank you so much, sir. Thank you so much for your answers. I am very happy that your lecture was so good. I am very happy, sir. Thank you so much.
Thank you.
Thank you.
I have one
Thank you for the
question.
GITAM University facilities also to providing this opportunity to directly interact with the Paul sir. Thank you so much.
Thank you, Sandesh.
Sure.
Yes.
Madam, please.
Dr. Samala, please.
One question, Dr.
One
Paul.
question.
Dr. Paul, actually, is the catalyst visible light active? Photocatalytic water splitting. You're doing the activity reported is visible light, right?
Yes, these are all visible light. Yes,
Visible
so not
light.
UV. Yeah.
Not
so
UV,
this is
not
the
UV.
challenge. Yes,
That is
correct.
the main challenge, of course. Yeah. Like
Yeah.
direct solar light. Have you tried?
We have tried some. So, for example, if we do full solar spectrum irradiation and measure the activity, but we almost always want to do just the visible portion of the spectrum, so we have an idea of the activity and the efficiency in that region specifically. So, I mean, typically, you know, going to 500 nanometers, 600 nanometers, that's what you want to try to optimize. Because one can always take and combine multiple materials, right? You can take and make a multi-layer solar cell where you put the lowest band gap absorber on the outside, right? And then the higher band gap absorber on the inside, and combine them all together, right? Or make stack configurations or make tandem cell configurations. And so one material doesn't have to be active across the entire solar spectrum.
Yeah.
We only need the materials that are active right now in the lower energy visible region. So I think that's why we focused on just that rather than the full solar spectrum.
Okay. Okay.
Thank you, Dr.
Thank you.
Thank you, Dr.
One
Magar.
question, Dr. Paul Magar. What is the maximum efficiency these copper materials have shown during your research, throughout your research?
Maximum efficiencies for a short time is on the order of 3 to 5%, on the order of this amount.
Okay.
As you saw, our photocurrents were around, maximum photocurrents were around 2 to 3 milliamps per centimeter squared. So maximum efficiency in this case, we should be seeing photocurrents more closer to like 30 milliamps per centimeter squared. So this is a challenge, especially for p-type oxides. There's very few, almost no p-type oxides that are efficient. So this is one reason to focus on them and to try to increase their efficiency. So we were quite happy with seeing a few millimeters squared to try to improve on it. Yeah.
Thank you very much for your fabulous presentation, Magad, and for the presentation, for answering all the questions. And any questions, anyone? No. Any more questions?
No, from my side, no.
Fabulous day, Dr. Magad.
Thank you.
Sure. Dr. Atmala?
Okay, thank you. Thank you very much, Dr. Paul Magad, for the excellent presentation. Now I request Dr. Venkatratnam sir to release the appreciation certificate to Dr. Paul Magad.
Thank you.
Yes. Yeah. And thank you for being an excellent audience.
Okay.
Sure.
Actually, we wish that COVID problem will end soon, and we want you to visit directly to, especially to India and to our university, Dr. Paul Magad.
Yes, please.
Yeah. And interact directly with our scholars, faculties. It will be great.
Please. Thank you.
Okay.
Thank you.
Thank you. Okay. With this, we will conclude today's second session, and we meet tomorrow morning sharp 9 o'clock in this with the theme of the presentation cybersecurity in chemical sectors by the experts Professor Clifford Glantz and Sri Nikhil Gupta Gaurishetty from Pacific Northwest National Laboratory, USA. Okay. Thank you.
Thank you.
Thank you all. Nice. For all the participants, e-certificates will be issued. Host can leave the session. Host.
It's fine, madam. Yes, madam. It's fine. Fine. Yeah. Okay, madam. Bye.
Okay, sir. Bye. See you tomorrow.